So I'm going to begin the presentation with a very short overview of the hemp and cannabis industry for those who may not be very familiar with it. This will allow me to describe the challenges and opportunities in this space and why I think it's important for us to be working diligently to develop methods for this space. I then want to discuss the selection of both the analytical tool and sample preparation tools that we will have, specifically for the analysis of cannabinoids. Then I want to change a little bit and talk about method development. Method development follows the selection of your tools and sample preparation. If you're lucky, you can find a method that's already developed. Some organizations like ASTM, AOAC have published official methods of analysis for cannabinoids in plant material. So if that suits you, your purpose, then you can adopt that. In that case, you would go through a method verification process. Otherwise, if you modify it or you're using it for a different approach, you have to go through a method validation. There's very prescriptive ways to do that, and so we'll talk a little bit about that and what we've done. Then I would like to introduce you to how we've used the EDGE and the mini LC in cannabis, specifically cannabinoid analysis. And we'll talk about the advantages of both the EDGE and the mini LC over traditional approaches. And then I'll show you some data specifically on edibles and looking at THC isomers using the EDGE and mini LC. And like every presentation, we'll finish that up with a conclusion and future directions. So what's the interest in cannabis? I had someone tell me once there's everything from rope to dope. And I kind of chuckled at the time, but there's absolutely no denying that there is a large number of applications for the hemp plant. The slide goes through some of them. One that's not listed that I'll mention right up front is the recreational market. And while cannabis / marijuana is still illegal at the federal level, there are states that have moved to legalize marijuana, which is a high THC varietal form of cannabis. They have moved to legalize it. Now, we also know that there are many uses for cannabis in the medicinal space, and supplements, healthcare applications are very numerous for not only the high varietal THCs, but some of the other varietals, including CBD and CBG and others that we'll discuss later. So this is kind of an emerging market, this medicinal supplements and healthcare, and certainly has gotten a lot of attention from our media. But there are a number of industrial applications as well for hemp. And matter of fact, these applications are some of the earliest applications in known civilizations. For instance, I think the earliest form of using cannabis was for parchment, so for writing, for paper. It's also grown, hemp was also grown by our forefathers in the colonial days, and it was used exclusively for the industrial applications of canvas, tarps, and rope to use in industrial applications. There are also applications in food sciences for food products for both human and animals. Consumer products are a big area of interest these days. There's everything from soaps and shampoos and lotions. And of course, you can't deny that there is this kind of agricultural and socioeconomic impact that this particular plant could have on our farmers. As recent as 2014, this was an illegal crop to grow, and only through the introduction of the Farm Bill, which legalized an R&D program for growing industrial hemp, could farmers take advantage of planting this particular crop to one day hopefully introduce it into commerce. Cannabis contains several different chemical classes. These include terpenoids, flavonoids, and cannabinoids. And it's these cannabinoids I want to speak to you a little bit about today, as they are very interesting from a number of different perspectives. One of the main reasons being is that these cannabinoids actually can interact with receptors in our bodies, CB1 and CB2. These receptors are part of what's called the endocannabinoid system. These cannabinoids in the cannabis plant are often called phytocannabinoids because they're not chemically the same as the endogenous cannabinoids in our body, but they mimic the behavior and interaction with the CB1 and CB2 receptors. The two most famous cannabinoids, or at least the likely two that you've encountered or heard about, are delta-9 THC. That's the cannabinoid that's associated with getting high. And then CBD, which is short for cannabidiol. And cannabidiol is typically found in low THC varietals, so that's found in hemp, industrial hemp varietals. And CBD has been studied very heavily for its neuroprotective benefits. And recently, the FDA has even approved a drug that contains CBD as its active ingredient for the treatment of two very rare childhood epileptic diseases. Now, these are certainly not the only two cannabinoids that are known. There are many cannabinoids that are found naturally occurring, usually at much lower levels than CBD and THC. I've got two examples of them on the lower part of the slide, CBG and CBN. CBG is being studied for some of its benefits with gut health, specifically inflammation in the gut. So irritable bowel and Crohn's disease are two things that they're hoping CBG can help with. And then they're also looking at CBN, which is shown there because it has some potential weight loss benefits, but most importantly, they're looking at it for some of its sleep benefits. So those are two naturally occurring cannabinoids that I call them minors because they're usually not as present as the delta-9 and the THC. And then there are also a number of cannabinoids that are not found in great abundance but can easily be synthesized and from hemp-derived components. The one that's really been abuzz lately is this delta-8 THC. Delta-8 THC is an isomer of delta-9 THC. The only difference is the location of the double bond, and it has very similar properties to THC. And then lastly, one of the most important discussions we should also have is the fact that these cannabinoids that I've been talking about are all found as neutral molecules, or I've been showing them to you as neutral molecules. However, the plant actually produces them as acidic forms, and I've actually now shown the cannabidiolic acid, CBDA, there, which has the carboxylic acid group on it. And through heat and other mechanisms, it can decarboxylate and turn into the CBD form, or the neutral form as they're called. So it is also important to note that when we go to look at these have slightly different interactions with the receptors, and also other physical and chemical property differences, and therefore should be treated as different ingredients from that standpoint. So as we go forward and start talking about what techniques we choose, it's very important for us to keep in mind that we have both acid and neutral forms present. So I included this slide to show you what some of the corporate projections of the global CBD market looks like between the time period of 2021 and 2025. It's projected to accelerate at a very robust CAGR, especially given the state of the pandemic economy. So it seems to be very robust. And then you couple that with the fact that I just spent the last slide telling you that there are more cannabinoids besides CBD, and they have other potential health benefits that are being studied. I think this makes this a a very exciting area to be in. Inevitably, you've all encountered some type of CBD product while you've been out and about in the retail space. There seems to be an ever-growing list of providers, offers, and places where you can buy these CBD products or hemp-based products. And while that's a good thing for the market, it does provide some challenges from a testing standpoint. First, there's a number of different ways that the product can be delivered via either inhalable, ingestible, or even topicals. And then the matrices that these products or that these materials are put into, the products that they're put into, they can vary wildly from everything from very oily to water soluble to high fats and waxes to sugars to dyes to fragrances, all potential interference when it comes to analyzing the cannabinoids themselves. And we've also seen quite a number of products introduced for both the human and animal product market. And so potentially that affects the approach that you take with the analysis being based whether it's on a human or an animal. So as we took stock of all of the analytical tools that we could use to measure cannabinoids, we decided that liquid chromatography made a lot of sense for a number of reasons. One is that it does preserve the ability to detect the acid and the neutral forms of the cannabinoids. Two, it's relatively inexpensive. And three, there were some methods that were already published, research methods that were already published out there. So we had the ability to hit the ground running when we started this. Although we still predated, at this time we still predated any official method of analysis coming from AOAC. So we had to basically look at all of the methods that were out there, select one, fine tune it for our particular application, and then put it through a validation process. So we were using Shimadzu HPLC with a ResTech ARC 18 column. ResTech had previously published I think 15 or 16-ish cannabinoids on this column using a very similar method. So we were interested in seeing if we could reproduce that. We had a total flow rate of 1.5 mils a minute. Our mobile phase A was water with 7.5 millimolar ammonium formate and 0.1% formic acid. And then mobile phase B was acetonitrile with 0.1% formic acid. Our oven temperature was 34 degrees C, and so this is if you're familiar with some of the publications or methods published by ResTech, this is very similar. A couple things you'll notice that are different here is that we operated a little bit different oven temperature, and we're also operating at a little bit different concentration of ammonium formate. We found we got a little bit better peak shapes when we did that. The wavelength is 228 nanometers. We did a 5 microliter injection. The method is 11 minutes, and as you can see on this chart, if my head wasn't in the way, we get these cannabinoids out in just about 9.5-ish minutes. For our calibration curve, and we use Cerilliant certified reference materials. We used 6 points that range from 5 microgram per mils to 100 microgram per mils. And I'll say right here that this particular spectra is one of the first that we did when we verified that we could reproduce the ResTech results. We actually don't run all of these cannabinoids all the time. We typically run 10 cannabinoids at a time. That's a matter of economics for us, and there's a couple of these that you just typically don't see very often at all. So we offer a 10 cannabinoid profile as our kind of our standard profile, and I'll talk more about that in a second. So armed with a method that we felt relatively comfortable with, we set out to do some method validation testing. And in order to do this, we follow the guidelines as established by AOAC for doing that. There are several different organizations who publish these types of guidance. They all are very similar to each other, and that's a good thing that there's so much similarity. So let me walk you through this very busy chart here, and I'll show you some of the data that we've got. So one of the first things we did was to establish our limit of detection and limit of quantitation for the method. And in order to do this, we inject the low levels of each of these analytes. These are the 10 analytes, the 10 cannabinoids that we're interested in analyzing. And so we do this, and then we can calculate the LOD, LOQ based on these traditional equations, where the LOD is 3.3 times the signal to noise, and the LOQ is 10 times that signal to noise. Maybe one of the more important factors that we look at is this resolution factor here. This R is equal to 2 times TR minus TRP divided by W plus WP, where this is basically the resolution, the ability of the system to separate two similar peaks. TR is the retention time of the peak you're measuring. TRP is the retention time of the previous peak. W is the width of the peak you're measuring. WP is the previous peak width. And so what you'll see oftentimes in some of these method requirements are values called out for, say, the difference between delta 8 and delta 9. So the retention time between delta 8 and delta 9 needs to be greater than 1. And as you can see here, we exceed that. Same thing, you'll see it often called out between CBD and CBG. It's 2. So we exceed the 1. It's oftentimes called out, but I'll show you some examples in a little bit where maybe this isn't good enough and we need to revisit our thinking there. The next thing we do is we check for the linearity of the method itself, and to do that we basically make a bunch of calibration curves over the period of a month, and we check their R squareds, and as you can see here, all of our R squareds are greater than 3 nines. So now we move on to the aspect of recovery, and to do that there is no accepted blank material that you then spike and then recover and do your recovery analysis on. So what we did is we ended up finding out about a program at the University of Kentucky where they were growing hemp and then sending it out to a bunch of labs for analysis, and then doing all the statistical analysis on that data, and then publishing that data and running that as a proficiency test program. And you could then buy that as a reference material. So it's a very well studied, well analyzed material. And so that's what we ended up doing, is not only joining the proficiency test program, but using that in our method validation efforts. So what we ended up doing is running a number of samples. This says mean of 4. That's 4 different sets of samples. It's actually each set was ran 3 times. So this is 12 different samples that were ran. Here's the averages. These are units of mass percent of these analytes here. Here is the expected value, or maybe better stated to say it's the published mean of the Kentucky hemp sample. And you can see our coefficient of variance on these analytes, and then the accuracy or recovery. So assuming that this expected value is 100%, that's how we calculated this accuracy or recovery. So we're pretty happy with these results. And so with that, we headed off to try to do some other interesting things with some new pieces of technology. And so now I want to kind of shift gears a little bit and talk about the project goals we have with Lucidity Mini LC and CEM Edge. So I'm very curious to understand the fit for purpose of the Lucidity Mini LC, and I'm also interested in how you could exploit the Edge for sample preparation in terms of cannabinoid analysis. So obviously, with our method being pretty robust that we've already worked out, the idea for the mini LC was to transfer the existing 10 cannabinoid method onto it and do some checking to see if all of the figures of merit still hold for the edge. So what we wanted to do there was we wanted to use our hand extraction method, which I didn't actually tell you about in the previous slide. I'll tell you about it in a second. So we have a hand extraction method. It's a solid liquid method. So we're going to use that as our truth data, since it matched so well to the Kentucky hemp samples. And then we're going to compare that to the edge test results. And then finally, we're going to try to show you some application of the mini LC and edge to the detection of THC isomers in edibles. And specifically there, I'm going to use a modified QueChERS as truth, which is how we currently do all of our edibles, and compare it with the edge results. So as you probably already know from Alicia's talk, the mini LC is a miniaturized HPLC that is relatively compact, and you can see a picture of it there along with the laptop that comes along with it for data acquisition. It does have 2 pumps. It has auto sampler, it has column oven, it has photodiode array detector. So it has all of the things you would think that you need for regular HPLC, just in a smaller, less expensive form factor. So obviously that's of interest to me. So we decided to take our method and run it. First thing we did was we injected our 10 cannabinoid standards along with an internal standard that you see right here in the middle. That's our internal standard. And you can see that that the lucidity system was able to detect all 10 of the cannabinoids. This is at 50 micrograms per milliliter, so that was very encouraging to us. So we then decided to do calibration curves, and I put the delta 9 THC curve here, which you can see is again 3 nines, a little greater than 3 nines. And it turns out all of the R squareds for all 10 cannabinoids were greater than 2 nines, and the resolution is greater than 1. So we pass all of the same figures of merit that you would expect our normal HPLC to pass. So now on to sample preparation. Sample preparation takes on many forms. It can be very simple. If you have a tincture, maybe you're just diluting it and shooting it. If there are other, the more complex the sample, the more complex the sample preparation, it seems. So I show 3 different types of samples here. This is raw material, bud material, if you like, plant material. This is a concentrate, a distillate that is full spectrum. So these are very high concentrations, very thick consistency of honey. And then everything over here, all the way over here is a final product. These are Delta 8 gummies that we tested. So this has Delta 8 in them. And for something like flour, we do a solid liquid extraction with methanol and vortexing and more vortexing and filtration and centrifugation and filtration. And all the way over here to these gummies, we use a modified QueChERS, and we'll talk about that in a little bit. And then in between, we might use something like a dilute and shoot method. When you do the gummies, these gummies, we dissolve them in water to begin with warm water, and then you add a slightly modified acetonitrile solution. Of course, that's miscible with the water that's in there. So you're getting a bit of liquid extraction going on at that point in time, because the gummy will completely solubilize in the water. And then you add your QueChERS salts and you get the layer separation out. And that's what you actually see here. This is actually a gummy that's been done by QueChERS. You can see the excess QueChERS salts at the bottom. You see this layer in the middle, which is a water layer, water soluble components are in there. Then you see this kind of in between layer. This is your layer that's probably stuck in between the organic layer up top and the aqueous layer below. And then finally your organic layers in the very top. That's where we would expect all of our cannabinoids to be located. So obviously, as I've followed the edge and the introduction of the edge into the market, one of the areas that has always been interesting to me is their use of this technology for a replacement for QueChERS, specifically for pesticide analysis. Well, I got to thinking that it might actually work well for our modified QueChERS and also even for our solid liquid extraction. So my thinking is, could we develop a method, a single method, or maybe a couple different methods depending on the complexity of the extraction, to allow us to automate the sample preparation for these samples that we have. I don't have to tell you a lot about the edge. It's probably been covered in detail and will continue to be covered in detail in this symposium, but it's automated, simple, efficient. It's a temperature controlled extraction. It's pressurized. You can modify it so that you have customizable extraction methods. It can run 12 samples in series. It is also software controlled, and so you basically set up your method and all the definitions there, which are your cycles, your parameters, your washes, things of that nature. Then the whole entire thing is automated, where the each Q cup is run in series. It adds the sample or pre-wets the samples. You can even add bubbles if you want to help with the agitation and mixing, which we did actually in one of our applications, and I'll mention that in a second. And then the sample is heated and pressurized, then it's completely cooled and filters out. And then, which is very important for us, it washes that entire fluidic pathway to ensure that there's no carryover from sample to sample. These cannabinoids are extremely sticky, and so it was very important for us to make sure we didn't have any carryover between samples. So the first project we started was just looking at results from flowers. Could we reproduce, could we say that the edge was reproducing the results that we were getting from our hand extraction? And that's what this crazy data set here goes into detail with. So let me walk you through it real quick. So this is actually work of one of the interns from Wingate University who worked with us for a summer on this project, and they did a really nice job. So here you can see there is these three samples. They're labeled 140, 142, and 154. Those are just internal lab numbers, and then they were able to calculate the recovery of each of these analytes. These are being our three most important analytes for us anyway, for flower. And so you can see that did pretty well there with somewhere between 114 and 101% recovery. Again, how we calculated truth is we assumed that our hand extraction method was true, and then we did the ratio of edge result to hand extraction result. All right, so since these look pretty good, we decided we'd take a little bit deeper dive into other minor cannabinoids that we saw. So we brought in the CBDA, CBGA, CBG, CBD, and we looked at all of those averages and standard deviations of those compounds. And again, the recovery looks very good there as well. And then finally, the intern did a 6-day precision test, trying to figure out which one is more precise, the hand extraction or the edge, and pretty close results there. So we were pretty excited by that. And so we were pretty convinced that the edge is able to replicate our hand extraction technique. Now remember, our hand extraction technique is pretty simple compared to our modified QueChERS, and this is our modified QueChERS, and I see my head's over part of it there, so I apologize for that. But essentially, with the QueChERS, you have to weigh out your sample, then you have to add water, and then you have to let that dissolve. And sometimes, depending on the size of the gummy or size of the particles that you've ground it into, this could take quite a while. And it's very important that you let them all dissolve in the QueChERS technique. Then you add your acetonitrile with a little bit of formic acid, you vortex it, you add your QueChERS salt pack, you vortex it again, you centrifuge it, and then you get that pretty picture that I showed you before. You then filter it and dilute it and run it. Where with the edge, our workflow looks a little differently. So we weigh out 0.25 grams of the powdered chocolate, or it says chocolate here. We started with chocolate, then we switched to gummies. Chocolate turns out to be a lot easier to analyze than gummies because the gummies are stickier. But you weigh out your sample, you then put it in the edge, you select your method, hit go, and then at the end you bring your volume up to 30 mils so that you've got a constant volume for each sample. Then you filter and prepare your dilutions like you normally would after QueChERS. So this is why this kind of sample prep was very intriguing to me, is because one, it could be automated, but two, it simplifies it. So let's take a look at some of the results. Okay, here are the results for the edibles, the gummies specifically. This data is from another student from Wingate University who came in to help us with this. And the goal of this project is to take a number of different gummy samples that contain THC or an isomer of THC, and analyze it and compare the QueChERS method to the edge method, and see if the edge method is comparable to the QueChERS method. And so what we did is we selected these 4 gummies, and we threw them in the freezer, -20 freezer overnight. We let them freeze as solid as we could. We then took them out, ground them up, and then divided the samples so that you could run one with QueChERS and one with edge. Right? So the student came in, did all of these samples, and then ran them. So these were all prepped and ran on the same day, ran on the same instrument, ran with the same calibration curve, ran with the same quality control samples. So this was as much apples to apples as we could get by literally trying to get a representative sample split equally for the QueChERS and the edge analysis. All right, the truth data was considered to be the QueChERS, and so that's how the recovery is presented. So as you can see, the recovery is actually pretty good between the edge and the QueChERS. It's seems to be biased a little low maybe for the edge, and I think that has to do with particle size. With the QueChERS, the whole entire gummy sample is dissolved, and so it's solubilized and then extracted, and that's a much more efficient extraction technique than a solid liquid extraction, which is what the edge is doing, because we don't solubilize the gummy in the edge, we just do the extraction in there. So I think if we paid attention a little bit better to our particle size, we could even tighten this up even better. So better cryo grinding is what I see here. I mean, these are good results for our initial thing, but I think cryo grinding is going to make that even tighter. The last thing I'd point out about this set of data is that is a trend that we're seeing, two trends. First of all, let's look at samples 15 and 16. You can see that they have mostly delta 8 and very little delta 9. And this is typical for a delta 8 gummy. A lot of times you will see these delta 8 gummies and they will have some amount of delta 9 in them. When delta 8 first hit the market, it was not uncommon to see up to 20% of the delta 8 actually be delta 9. So over time that has improved, significantly if people either cleaned up their samples or figured out more complete synthesis methods. However, we're not now noticing there's a trend from formulators to introduce what they call hemp-derived delta-9 THC. And so that is THC that is derived from delta-9, and they are infusing that into products. And so 0012 and 0045 both contain much more delta-9 than the sample 15 and 16. And this is on purpose. They're actually going back and fortifying these samples with hemp-derived THC. And we're able to see that. And I threw the ratio of D8 to D9 up over here because you can quickly pick up on which one's been fortified and which one has not, looking at the ratio. I could not talk about D8, D9 without issuing a word of caution. So this particular slide kind of shows an example of some of the things that we've seen with testing some of these samples. So this particular line here, this purplish pink line, is the actual sample itself. The black line, the black trace, is the chromatogram from our standard. So these are our standard reference materials. You can see D8, D9, CBN. So I've zoomed in real close right here where you can see. And as you can see, just using 228 nanometers, this is the kind of resolution that you get. This sample looks really, this guy right here gives me no concern, no pause, right? I mean, I'm good to go right here. Certainly much greater than the required resolution between those two peaks. However, you notice that the sample actually contains this peak right here, which we do not know what that is. It also contains some contaminant here, maybe even some contaminant here, and maybe even a little CBN there. So whatever this product is, it has several things in it. I can positively identify the delta 8 and quantify it. But as you notice, it's running, it's kind of got this leading edge that's kind of smushing up and really hampering my ability to detect delta 9 THC. So a little bit of word of caution there, and I certainly am open to discussing why we think this happens and figuring it out, and maybe getting some more information out in the public domain as to why this is happening. So if anyone wants to collaborate on that, I'm very much interested in doing that. I think we know that a politically correct statement would be, this isn't cleaned up as well as I would like it to be if it were my sample. So moving on to some conclusion slides, I hope that gives you an overview, good overview of our cannabinoid analysis and how we're integrating in different THC isomers into our analysis. So let's just make some concluding remarks. The number of cannabinoids and the sample matrices continue to increase. So we're not just seeing THC delta 9 and delta 8. We're seeing delta 10 THC, the RNS enantiomers. We're seeing THCO, THC acetate. So we're seeing a lot of different THC isomers. And as you introduce more and more of these isomers, you got to then be very concerned about your analytical performance with being able to discriminate against the other cannabinoids that might be present. So having a good idea of what you're analyzing and how that impacts your analysis is going to be critical. Even if your method, as I demonstrated, my method clearly passes all of the checks for resolution, but some of the samples, when we run them, we see a detrimental effect in our ability to detect delta 9 accurately. So we've had to make adjustments to the method to continue getting the results that we need. All right, sample prep's always a bottleneck. automated sample prep, it's always a good thing because you can automate it to reduce the errors from users. And ideally, it improves reproducibility because robots are better than humans at that. Edge has demonstrated its ability to do a wide range of sample prep, from the easy flower stuff that we did to the more complex gummy samples. I think the Mini LC demonstrated that it can easily run our 10 cannabinoid method, which gives you 10 cannabinoids in about nine and a half, 10 minutes. And that includes the two THC isomers that we were talking about today, which is the Delta 9 and Delta 8 THC. But again, I want to come back to the fact that fit for purpose is really the key to any of this method development and validation. So, and with that, I want to get off the stage and say here are my co-authors, Viviana, JC, and Veronica. Rachel was our intern from Wingit, who did the initial edge work. Daniel Rumley is my current research student from Wingit. And then I really could just list the whole entire crew at Lucidity and CEM. They're always very helpful and very quick to pick up the phone and come over and help if I've got problems. So, but specifically, Alicia, Brittany, and Dan have been very valuable in helping us get to this point. And with that, I'll thank you.
Thank you, Todd, for this exciting presentation and for sharing the work that you're doing in your lab. As a reminder, to submit questions, please type them in the space provided and click Send to submit. We will now begin our question and answer session. In addition to Todd Griffin, we are joined by Dr. Alicia Stell, Product Manager of Organic Solutions at CEM and Lucidity Systems.
All right, so the first question that we have, thank you all for your attendance and for asking questions. We've already got a couple of them coming in. First question we have is, Todd, it looks like this is for you. What is the gradient used in the method?
Yes, so we use an isocratic method. It's not actually a gradient, and it is 75% organic, 25% aqueous. And of course, as I mentioned in the slide, the aqueous is modified with 7.5 millimolar ammonium nitrate and or ammonium formate rather, and formic acid at 1.1%. And the organic layer is acetonitrile with 0.1% formic acid.
Okay, thank you for that. Our next question is, which sample benefit from adding bubbles? Which samples benefit from adding bubbles?
Yeah, that's a good question. So Alicia and her crew actually recommended that we try bubbling when we were getting some low recovers initially on our gummy samples. And it seems to me, and Alicia, you might can chime in here, but it seemed to me that bubbling actually helped with just the mechanical agitation of making sure you had good contact between the particle and the solvent that was that was involved in the extraction, and that seemed to bring our recovery up quite a lot.
Yeah, I can add in a little bit there. That's exactly right, Todd. It's more about just making sure that you're interfacing with that sample properly. So bubbling is going to be most applicable for smaller sample sizes, for samples that you have a sorbent in there. I don't think sorbent was used in any stuff we've been talking about today, but say you did have some C18 or PSA or carbon black in there, bubbling is going to really help that interface with the sample as well. And if you just kind of think about it, like as long as a little bit of like light bubbling is going to move the sample around, then it's probably going to be advantageous. A situation where bubbling may not be as applicable is if you say have 30 grams of soil, right? You've got so much soil, really a little bit of bubbling is not going to do anything to move that around any. So you kind of think about your sample, but in a lot of cases, especially the cannabis industry, those samples are going to be well versed to lend themselves to bubbling.
Excellent. Thank you, both of you. The next question, I believe, is for Alicia. We have an audience member wanting to know if you can run gradients on the Lucidity LC.
Yeah, that's a really good question because when I talked earlier today and Todd just talking now, we both ran isocratic. So that's what was applicable for the applications that we were discussing at that time. But yes, you can run a gradient. It is a binary system. So you've got two pumps, you've got two different solvents, and you can run a gradient with those particular solvents as you would in any normal HPLC application.
Excellent. Well, thank you for that. Um, let's see. I am not seeing any additional questions coming in. So if you do have questions, I'll give maybe one more minute for the audience to be able to ask their questions right now. Alicia, is there anything that you wanted to add, or Todd, after the conclusion of this presentation for our audience?
I just want to thank Todd for coming in and giving that nice talk. I thought it actually paired really well with what I talked about earlier today. So I just, Todd, thank you for that presentation. And
Yeah, and likewise, Alicia, it's been a real pleasure partnering with you guys and working on this collaborative research.
All right. Well, thank you to both of you. Looks like we have satisfied everyone's curiosities. And so with that, I'm going to bid everyone thank you for joining us today. I want to remind everyone that Dr. Rhonda Gross and Dr. Nick Snow will be presenting next week on Wednesday at 11 a.m. and at 3 p.m. So please be sure to join us for those two sessions. Thank you for attention today, and we look forward to seeing you next week. Bye.
bye.